Hello class, today we'll talk about chapter 8. Chapter 8 deals with friction. The first two sections will be covered in this lecture. As you know, this lecture is pre-recorded and we'll meet again on Thursday to continue the discussion. Now this section, two sections, is very important. I cannot cover everything in this presentation, so I have posted an assignment that include the 3 problems that are already solved from the textbook. Please go over them after we finish this presentation. So the chapter talks about the dry friction and problems that involve dry friction. So the objective is first to understand the characteristics of dry friction and try to understand how to solve problems that involve friction. Friction is a force that resists the movement of two contacting surfaces that slides relative to one another. This force always tangent to the surface at the point of contact. And therefore the answer for the first quiz reading is friction forces always act parallel to the contact surface. The second reading quiz is assuming that there is a block at stationary position, meaning it doesn't move, then the friction force acting on it is always less than mu Sm. This is also called the maximum static friction. So the answer is A. The application of friction can be found in different fields. For example, in mechanical engineering, where you are concerned about the design of a mechanism such as a bicycle, you might be interested to find how much of the friction force required to be applied on a bicycle tire to stop it from rotating. Another example is a fridge. A person trying to pull the fridge horizontally, and the question could be, what is the pull downward force such that the refrigerator starts slipping on the floor? Or it could be, what is the height that should be that the fridge should be pulled from such that the fridge doesn't tip? Let's consider a box that has a weight W, and this box is sitting on a surface as a horizontal surface. Assume this horizontal surface is not smooth, meaning it creates some friction, where the friction is defined as a force of resistance acting on a body with direction opposite to the direction of the motion. So in this example, if there is an external force with a magnitude of P is pulling that object to the right, then we expect the resistance comes opposite to that motion, so the resistance will be in that direction, right, opposite to the motion of the box. Experimentally, this frictional force is always acting tangent or parallel to the contact surface, and as we mentioned, the direction always opposite to the motion, or the tendency to the motion. The scenarios that this box could undergo assume that the value of the load P starts from 0. So experimentally, you will observe that the box will not start moving immediately after the value of the force increase from 0 to an incremental value higher than the 0. rather than it will start moving at a certain value. during 0 until that certain value, there is some friction force generated, and that friction force, which we call it F, prevent that object from moving. However, when the p-value increases beyond a certain value, which we will discuss, the object will start moving, and you can try it at home. Let's draw the free body diagram of the forces acting on the object. Now there are the weight, which is always assumed to be at the center of the geometry. We have the external force. We have the normal force. The normal force is definitely, because we have a surface, it's distributed. Typically, this distributed normal force can be represented by an average single force somewhere along the base or along the contact area, and we'll find where is that equivalent normal force should be, again depending on the problem statement. Now the last force is the friction force, and the friction force, as we mentioned, is always tangent to the contact area, so and opposite to the direction, so it's moving to the left, because the tendency of this object is to move to the right. Now, depending on, again, of the problem, if this box or this object is moving to the right, we could assume that the reaction force is somewhere to the right, simply because knowing that the P force tends to tip the object in that direction, the clockwise, and that would reduce the amount of reaction force to the left side. So therefore, we expect that the average or the equivalent force of this distributed load somewhere to the right of the center of the object. So we assume it to be over here. And since this assumption requires a quantitative value, or also requires us to validate that assumption, we will begin by assuming that the reaction force N is located at a distance x from center of that object. Now the force, the friction force, is tangent and it's a free vector, so it could be anywhere along here. So we choose to apply it at the same node where the reaction force is at. Also, geometrically, the force P must have a known position relative to a reference. Let's say it has a value of h. The dimensions or the width of this block is a, so half of this distance is a over 2, which represent the center of the gravity, which is the centroid. So for the body shown in this figure to be under equilibrium, two things has to happen. First, all the forces should be equal to 0. This will prevent the object from translating in x and y. And the second is the moment about any point, such as point O, must be 0. And by applying these two conditions, especially the moment, we'll find out that the moment produced by the weight, which is, let's say if we apply the moment about O, what we'll get is W multiplied by x, and this is counterclockwise, must be equal to the moment produced by the P, which is h multiplied by P. So this equilibrium equation, right, will determine the location of x together with the summation of x and 0, summation of forces in x and summation of the forces in y equal to 0. Where summation of x equal to 0 will produce F must be equal to the P, and summation of forces in y will produce that N equal to W. Now, to better understand what's really happening to the friction force between the surface and the object, let's assume that the configuration of the system over here is such that the object doesn't tip about a point O over here. It doesn't tip. So by examining this, we mean that the value of the force P incrementally increases. As this force P increases, we expect that the friction force will start to generate the contact, and its magnitude will increase proportionally equal to the magnitude of P, and which is represented in this graph. Assume that we start increasing the value of the external load, the value of the friction F will increase, and that relationship is assumed to be equal to 45, and assuming that this relationship has a 45 degree, simply because the forces must be equal to the P, and this is a linear equation that has an angle 45. Now, as we're increasing the force P, there is a point at which the value of the force will drop from a maximum value, which represent Fs, where Fs is the maximum static friction force. After that force, the friction force will drop to another value, and that value is called a kinetic. And that's something you can feel when you try to push an object on a flat surface. You'll feel first that the resistance is proportionally increasing with the amount of force that you're applying, and then once the object starts moving, this force will, or this effort will drop a little bit. The Fk is called the friction of the kinetic force, and Fs is called the static friction force, and both of them are proportional to the normal force. The difference is the proportionality depends on a value called mu s, which is the coefficient of static friction for the static friction force, and mu k is dynamic friction coefficient for the dynamic friction force. In summary, what's happening is the maximum friction force, which is the force just before the block begins moving, and we call this moment and impeding motion, correspond to a maximum value of the friction, which is Fs equal to mu s multiplied by the normal force. In the graph, this value is over here, and then once this object starts moving, the friction will drop to a final value of k. For small load, this final value will be constant, and we'll assume this value to be equal to mu k multiplied by n, which is called also mu k, called the kinetic friction coefficient. It's worth to mention here that one common mistake is to assume that the friction generated between the contact is equal to mu s n. So this is a wrong assumption. In fact, that value is the maximum friction force before the object starts moving. So the friction F could take any value from 0 until the maximum while the object is not moving. The coefficient of static friction, mu s, could be experimentally computed by using a block on an inclined surface where that angle, as we will see later, is going to be equivalent to the phi s. Phi s here refers to the angle between the normal force and the resultant force, which is computed from the two vectors friction force S and N. The tan of the angle phi S in this figure is equal to the opposite Fs, which is the maximum friction force, divided over the normal force, and that's gonna give you the value of mu s, simply because Fs equal to mu s n divided over n, and that's gonna give you a mu s. So therefore phi s can be computed by solving this equation, which is a or r tangent of mu s. A simple experiment could be constructed to compute the coefficient of friction or the coefficient of static friction. As we mentioned, we put a block on an inclined surface where the angle of the surface is theta s. Now, drawing the free body diagram of this ideal system will give you a weight pointing downward with an angle theta s. Friction force is opposite to the motion, so this tends to slip downward, so the friction force is to the right. The impeding friction is when the friction force is maximum at the maximum static force Fs equal to mu s n, and the normal force is always perpendicular to the surface. Assume that the x direction is horizontal and the y direction is perpendicular to the surface. This will make the problem easier to solve. Now, summation of forces in y will give us the following. Will give us, because this is our y, it's going to be n minus the component of w in the y, which is w cosine angle, and that's a negative, equal to 0. And with that you can solve n. And second, the summation of forces in x equal to 0, so we'll have the component of w, which is going to be going to the downward, opposite to the x, so it's a w sine theta, and it's a negative, plus mu s n, and that's equal to 0. So solving these two equations will lead us to a relationship between the mu s and tan theta s. So with that you can see that the mu s can be computed or can be found when the object start to move at an angle theta s. Now, solving the problems with dry friction is a little bit tricky, I must admit, and for you to be able to solve correctly, you must do a lot of exercises. The textbook has a few examples that I recommend everyone to go and look at, and also discuss in depth different scenarios where the dry friction could be assumed with slippage or with a tipping. Now, in general, the procedure that I recommend you to follow is first to draw the necessary free body diagram. This involves showing all the friction forces in the correct direction, and which is always opposite to the motion or the impeding motion. Also, determine the number of unknown. You should not assume that the maximum, or you should not assume that the friction equal to mu s n. This is only when the object is impeding, meaning it's about to move. Apply the equation of equilibrium and solve for the unknowns. Before we start with a problem, or with an exercise, let's look into this note. There is a concept called slipping and tipping. An object that tips mean that the object will rotate about a fixed point. For example, this cabinet, if pushed by P, this object could tip about the corner and causing this object to rotate clockwise. A slip means the object doesn't tip, but rather it's slipping in the direction of the force applied, and this instant the force or the friction force is opposite to the motion, which is to the left here. Now in both cases you have a normal force. The location of normal force for a sliding or for a slipping conditions is located somewhere on the ground and must be within the geometry of this box. So if we assume it to be x, then this x should be somewhere in the right half of this object when the P is acting or when P is pushing the object. However, in tipping, the object will tip about the corner, meaning the corner act as a pivot, and therefore this means that we have two forces, and these forces are the friction forces, which is horizontal, and normal forces, which is perpendicular. Now the amount of force here must not exceed the maximum static friction force, because if it does, then it means that the object is not tipping. In the left side hand, the force or the x must not exceed the b/2, because if it does, means that the object will be tipping. Let's take an example and explain this more in detail. These conditions summarizes the slipping and tipping. For the slipping, as we mentioned, you assume that the friction is maximum and it's equal mu s n, and what we wanted to solve typically is the x, the amount of P at which the object will start slipping, as well as the normal force. So this is altogether is three unknowns with that assumption. Now we always have to check for the slipping condition, which we said that x must be located on the halfway of this geometry. Now for the tipping to occur, we always must assume that the tipping happens at the corner. If we do that, we solve for the unknown P, N, and F, and then we check if the force that we computed is less than the maximum, and if it is less, then tipping will take place. To summarize that in an exercise given in this example, a crate that has a weight of 250 pounds, the coefficient of static friction is known to be 0.4, and that again can be experimentally be calculated, and it depends again on the material of the surfaces and the surface conditions, such as, is it wet or is it rough. Now this example asks us to find the maximum force P that can be applied without causing this object to move, and the movement are classified into two. Either it's going to tip about A, or it's going to slide along the surface. So the first step is simply to draw the free body diagram of this object. We have a force at a known height, but it's unknown as a magnitude. We do have a friction force opposite to the direction of the movement, which is assumed to be to the left. We have a reaction force somewhere. It could be at X, or it could be at the corner, and the normal force is unknown. So also, or in total we have 4 unknowns, but 4 unknowns are more than the 3 equations that we can obtain from equilibrium equation. So we must impose some assumption and check this assumption if they are valid. So the first assumption to be examined is, let's assume the crate is slipping. By that, what we mean is this object is at the verge of moving, which means the force is maximum, and that is equal to Fs, which is mu Sn, and mu S is given to us. So the problem will be reduced into 3 unknowns with 1 dependent, or 4 unknowns with 1 dependent, so we have a total of 3 unknowns. So with that assumption of the slippage, we continue to apply by applying the equation of equilibrium on the object. So we start with summation of forces in X equal to 0, so P minus the friction 0.4 N and equal to 0, and the summation of forces in Y equal to 0, which is N minus 250 equal to 0. This will lead us to 2 magnitude, the force P, the maximum that could cause the slippage, and the reaction force N. Now the question is, where is that N is located? Now we said for the this to slip, N must be between 0 to 1.5. Now let's check that by applying the moment about this point O. Assume this is the point O, right? So applying the moment, so we have to calculate the moment of the weight and the moment of the P. The moment of the N and F are zeros because they intersect with O. By doing that, we have the moment of the P, which is counter or clockwise. It tend to rotate the object in clockwise, so it's a negative 100 by the distance 4.5. P is equal to 100 as we found here, plus the moment of the weight, which is counterclockwise, so it tends to rotate the object in that way. So it's 250 multiplied by x. Solving that will lead us to x equal to 1.8. Now 1.8 is greater than 1.5, so it's according to the assumption this O is located somewhere outside, so this is invalid, so meaning that this object will not tip. Another way to say it, that the P, as we are gradually increasing the force P, before this object starts slipping, it will tip, and because simply for that to slide or to slip, the X must be or is calculated to be outside the geometry of that box, so slippage will not occur. So the second assumption that we should examine is tipping. Now definitely because the object is not slipping, then it must be tipping. Let's verify that. Now tipping happens at the corner, at this corner. So imagine tipping is such as a point or a pivot where this object will internally rotate about this point O. Now we apply the equation of equilibrium. We have 3 unknowns, F, N, and P. The X location is known. It's equal 1.5. So simply Applying the forces in x equal to 0 will lead us that P minus F equal to 0, and second equation is that summation of forces in y equal to 0, so 250 minus 250 plus n equal to 0. These together will give us that the value of P equal to the F and the value of the normal force equal to 150 pound. Now, to calculate the amount of P or F, we can use the moment about point O. Moment about point O is equal to the moment of the 250 and the moment of the P. Now, the moment of the P is equal to negative 4.5 multiplied by P plus the moment of the weight, which is 250 multiplied by the distance 1.5. This is all equal to 0 because it's at equilibrium, it's about to tip. So solving this equation will give us a value of 83.3 pound. Now, this value also, plugging it here, and this equation will give us F equal to 83 also 0.3 pound. Now, the condition for tipping, it must be that the friction force must be less than the maximum static friction force. The maximum static friction force, which is mu s multiplied by n, so it's mu s was given to be 0.4 multiplied by n, which is 250. So 250 by 0.4 is 100. So therefore 83 is less than 100, and that's the condition that satisfies that the object is tipping. So therefore the solution is second solution, which is tipping, and these are the magnitudes. Let's take two concept quizzes. Then the first one, assume that we have an object, have a 100-pound weight, and we want to know what of these three forces that have equal magnitude but different direction, which of one of them requires the least force to begin sliding. Sliding means the friction force F opposite to the impeding motion, which is to the right, and knowing that this to start moving is going to be equal to the 0.4 multiplied by 100, and that must be equal to the force, right? Now, force, we mean by that the force that is in the same direction. So if we choose P, then directly this is going to be equal 0.4 by 100. If we choose P within an angle, then we have to add a cosine, let's say cosine angle, right? Cosine angle. So choosing B, for example, that's going to give us 0.4 by 100 over cosine that angle, which means you have or you need higher magnitude. So therefore the least force that required to have this object to start moving is the one that has a zero angle. So the answer is A. This ladder shown in this graph is sitting on a surface. Because of its weight, the ladder tends to move downward. The friction force at B is opposite, or first is tangent to the ladder and opposite to the motions. So this is going to be your friction force. So the answer is C. The last example I would like to show in this presentation is the group problem solving. The purpose is to give you the idea. You can work on it at home. off and look at the complete solution. To begin with, let's understand what's happening or what's the requirement. Given here a vehicle that has a mass of 200 or 2000 kilogram, and friction between the wheels and the ground is 0.3. We want to find the smallest magnitude of the force F that requires to move the car if the back brakes are locked and the front wheels are free to rotate. This is very important to understand. The back wheel locked means doesn't rotate, meaning that there exists a friction force opposite to the impeding motion, right? And definitely we know there is a normal force here, let's call it NB, as a result of the reaction of the weight. We know also there is a weight at the center of the gravity of that vehicle, and that is equal to 200 multiplied by 9.1, right? So we're trying to draw the free body diagram. And the second set of the unknown forces, in fact, we have a reaction force at A. However, we don't have any friction force because this wheel is rotating. You know, the rotation of a wheel on a surface doesn't produce any friction force simply because at the contact, the velocity between the wheel and the ground at the contact is zero because there is no relative velocity. So therefore, there is no friction force at this point. So this is the free body diagram, including the force F. So what we want to do is find the smallest magnitude. So the smallest magnitude meaning when this object starts to move. So we must assign the force or friction force to be maximum friction force, which is equal to mu s multiplied by the NB. So this is how many unknowns we have. We have F, NA, NB, right? 3 unknowns, and the last unknown, which is Fs, is dependent on NB. So total we have 3 unknowns, and we can solve it by equation of equilibrium. So the solution is simply given here. You can take a look at the presentation for completeness and verify your answers. So the answers for the minimum force required to move this vehicle is going to be 2762 Newton, with the reaction force and the friction force calculated from the equation of equilibrium. There is an assignment. The assignment I uploaded has some examples already solved in the textbook, but the purpose is that you go over them and try to understand them more in depth. It requires some time to understand, so please pay more attention and read the section 8.1 and 8.2. With this, I conclude the presentation file or presentation for today's lecture. I will see you guys on Thursday, and remember that we have an exam on or after Thursday.